Hi, in this video, I'm going to go through this example in which we train a model-based policy optimization agent from the reinforcement toolbox, reinforcement learning toolbox of MATLAB. And the special thing that this agent has is that it models the environment. So basically, this agent is going to be used in this example to balance a vertical pole on top of a cart that you basically move left and right to keep it balanced. We have seen that in other videos, but the special thing in here is that there's going to be in the agent a deep neural network to model the environment. So you're going to see at the end that with accuracy is able to model the physical dynamics of the environment of the cart. And with that, you get more experiences to train your agent. I mean, your agent in this case is going to be a soft actor critic. So there's going to be so basically once you train this model, then you say, okay, I want 20% of experiences coming from the real environment, 80% from my model. And yeah, I'm going to show you at the end that is pretty accurate. Okay, so let's go to the example by clicking here. That takes us to the desktop here, and the first thing is loading the environment, which we have seen before. It has the usual suspects of the mass of the card, the pole, the length, also the reward of -50 for falling, then the penalty for falling of -50 and reward for not falling, the threshold for the angle and the maximum force of 10 newtons, etc. Okay, so the observations are the same. We're gonna have 4 elements for the position of the card and the angle of the pole, and also their corresponding derivatives. There's corresponding horizontal and angular speed, and the action is gonna be just the force. But notice that we have numeric spec for the observation as always. But since we're going to use the soft actor critic, we can which tolerates continuous actions, then we're going to use a numeric spec for the action. So it can have any real value between -10 newtons and 10 newtons. Okay, so now let's create the SAC. I'm going to go briefly to the SAC agent. I'm going to put the description, this article in the description of this video. So the SAC agent can tolerate both observation, continuous or discrete, and the action can be continuous. And the critic is going. I mean, this is an. Let's show it first relative to other agents in reinforcement learning. So I'm going to go to that article, and you can see here. Yeah, the machine is a little bit slow today. Okay, I'm trying to scroll a little bit down. Okay, you can see here that the soft actor critic is of policy. It trains without the policy, and has an actor and critic, and basically action space continuous as we saw. And the functions that it uses for the critic is just use an RL Q value function, a regular Q value function. But for the action, it uses, let me scroll down a little bit. It uses the RL continuous Gaussian actor because it basically is going to use a Gaussian distribution for the action. And we're going to see that in the SAC agent article. Okay, so you can see in here that the neural network is going to take as input the observation for the actor, and the output is going to be the mean and standard deviation, and it's going to use a Gaussian distribution. And from that Gaussian distribution, we're going to clamp it between -1 and 1 with a tan h function, and then scale it to the actual forces that we desire for the action, which is -10 newtons to 10 newtons. Okay, so one of the things to highlight of this agent is that as other agents, it uses a circular buffer experience, which is usually a bunch thousands of experiences, and from that you sample a mini batch of size specified in the options of the agent. And also it has the concept of entropy. So basically the entropy is used for exploration, and basically you try to maximize the reward, but at the same time you want to be close to a target entropy. And yeah, also has the Gaussian output that I just showed. Okay, so the way that it trains it for the q value function to estimate the long-term reward is as the other agents that we have seen so far. It basically try to minimize the error between the expected long-term reward that is obtained from a combination of the rewards that you have accumulated so far in the episode, and also the target function. Notice that in this agent has another thing special, is that has multiple critics, and they have the k value. So in this example, the k is gonna be 2, so you're gonna have 2 critics, and those 2 critics can have different architectures. But notice that for each k, there's a kt. So there's a target. So this concept we have seen in other agents, that you have a critic and a target critic. And the target critic is not trained as often. The one that is trained often is the non-target. And then after certain time, I'm going to show the target concept. Here's at the end is the target concept. A certain frequency configured by this parameter, the target gets a copy of the non-target network parameters, and you can mix them with a smooth factor. So notice that in this case, that happens for each critic. So each critic has its corresponding target. So that for each critic, there's a corresponding target that has the same architecture, but doesn't have the same weights. So the purpose of the target is that you estimate the long-term reward, and you do it here. You take the minimum k. So basically it's like a cross training, because notice that for training critic number 1, I may use critic number 2 to get the long-term reward. And also I use the entropy as long with this weight factor, and this weight factor for the entropy is configured in here. This is another option from the agent. Okay, so once I have the long-term reward, I basically can compute the loss, and I try to estimate better the long-term reward for that agent. For the actor, I try to do 2 things. One of them is to maximize the reward, but here is minimizing this function because I put the negative of the long-term reward, so that's in that way I maximize the reward. And I also add the entropy factor as well, so trying to maximize the reward with some entropy. And then I try to also minimize the error of the entropy. So I try to approximate this entropy, and this entropy is configured in this entropy weight options. Yeah, that's one of the parameters, but there's another one. Yeah, exactly. The h you specify here, and the alpha you specify in here. This is the alpha. Yeah, this should be the alpha, and this should be the h. Okay, so basically you're trying to get close to the entropy while maximizing the reward, so that way you encourage an exploration strategy. That's how this agent implements the exploration strategy to try to land in the global maximum of the reward rather than local minimum, where you most likely will land if you have solely a greedy exploration strategy. Okay, so going back to the example for this, okay, so we created already the environment, and for the soft actor critic, we're just gonna specify the options. We're gonna specify notice that we're gonna use a couple of critics. Those are the Ks that we saw in the article, and the actor is gonna have its own neural network, so all of them are gonna have the same learning rate. The initialization options, we're gonna use a default network for them. We're not gonna create the network. The agent provides one for you if you don't specify it. So we have to specify the observation information, the action information, these initialization options, and the agent options. The mini batch size is gonna be 256, and I guess it's using the default size for the experience buffer. And the number of gradient steps is per update is basically the how many times you run the loop for computing the gradients for the networks, and you can see that in the documentation. Okay, so once we have the agent options, we're gonna create the base agent. well, we have the base agent here. We created in here with the RL SAC agent. So yeah, we created in this line. So we already have the SAC agent, and then we just further modify its options manually in here like this. Although we could have done this by creating an options object and just pass it in the constructor of the class. You can do it either way. Okay, now the interesting part of this example, which is basically modeling the environment. And for that, they have the concept of transition functions. So you have a function when you model the environment, if you notice in most or all these reinforcement learning examples, you have a reward, an observation, and a boolean indicating if the episode finished or not. And those are three scalars that you can easily model in a deep neural network. So basically the concept is that you have a neural network that outputs a scalar for observation, and you can have it for reward and for the termination function. But in this example, since the reward function can easily be computed with a simple formula, and the determination function is easily computed with a formula, you better use the formula because it's going to take more time to train if you put a neural network on them. But the observation is harder. You don't have a formula for the observation. So for that, we're going to create a neural network that's going to take as input the current action and observation using, as always, a network of fully connected layers and ReLUs that outputs the observation. So it is not sufficient to only have one model for that. So the strategy that I do for this training is, as they have the concept of trajectories and the horizon. So in here you can see that this is one trajectory is one row in here. So you can see that you use your agent, your base agent, to give an observation from the environment, give me the action that I will take for the observation, and then they feed it to the model, and the model is going to give you the observation, the reward, which is your experience set. An experience set is reward, observation, and is the simulation done. So once you have that experience tuple, then you select another model, because in this case we're going to have three models, and then you randomly select for this trajectory. You select one model. I select them. Select model number 3. And then you feed that to, again, the same agent, create the next action for the new observation, and get a new experience, reward of new observation, and new termination signal. So at the end, those experiences are accumulated and put into a repository. And that's a trajectory. And notice that the horizon is 2 in here. It means that I'm going to use 2 models. If I had horizon 3, then I would use another model. I feed it to another model. So the second trajectory is going to do the same. Randomly select model 1, get another experience. Randomly select model 3, get another experience. And you can have, in this example, we're going to have 20,000 trajectories. So we're going to have like 20,000 rows down like this one. For the columns, which are the horizon, it's going to start with 1, and there's a way to configure the agent to start with 1, and gradually, after 100 episodes, increase the horizon to 2 so that you can have 2 models, and then increase the horizon to maximum 3. That's the configuration that we're going to use in this example. And notice that all of these experiences are stored in this repository, and at the end you configure, I want to use 20% of real experiences and 80% of the repository of experience generated by the internal model of the agent. Okay, so now first we're going to create the model for the environment, and that is done through lambda functions. So in the lambda function, you can put any function that you want, but for the observation, we are going to use a neural network. And we're going to use this function from the example to create a neural network, and this function is from the reinforcement learning toolbox to create the continuous deterministic transition function based on a network. So you have to pass the observations and the actions, which are the inputs to your network, and you have to indicate in the network what are the input nodes for the observation and action. And this will be the output. The output is the next observation. So let's create the network for the first one. Okay, I'm gonna put a breakpoint so that we can see what happens in there. In the creation of the network, it's gonna be very simple. You're gonna have as the input layer, you're gonna have the observation, another input layer for the actions, and then you have a concatenation layer for the common path that you're gonna take the two inputs, the observation and actions, and then that is followed by fully connected layers, ReLU of size 64 hidden units, and at the end, the final fully connected layer is gonna have a four observations, because the output has to be the same size of the observations. We're gonna have four outputs for each observation. We're gonna model the observations, and then all those nodes are gonna be placed in a layer graph, and we just add the layers to the layer graph, and then concatenate the observation with the input number 1 of the concatenation, input number 2, and then wrap the layer graph into a DL network to have the neural network. Okay, so let's do that and quickly see the network. Let's take a quick look, and we can see here the two inputs. Some other networks have some fully connected layers in here, but this one doesn't have fully connected layers in the branches, and the output is going to be size of 4 for the 4 observation. That is the position, angle, and their corresponding velocities. Okay, so we have that network to model the observation. So we're gonna have 3 of them. We're gonna have 3 of these networks, because we have 3 models to choose from in this strategy of modeling. Okay, so we pass that network. Yeah, but for the reward is so simple, and you can see that we have a reward for not falling of 1 and penalty for falling -50. And in this case, we're gonna have distribute the reward for not falling. Half of it is gonna go from regular, and half of it is gonna go from the distance from the threshold. And for the indexes where you're not terminated, you're gonna get the positive reward, and for the indexes where you're terminated, you're gonna get the negative reward. And the termination index is obtained from this other function that basically computes the threshold of the angle. And if you are beyond the threshold, horizontal threshold, or beyond the angular threshold, then you're terminated according to this function. So this function is used inside of here to determine if you're terminated or not, and then that computes the reward. So that's the function that we're gonna use. We could use a neural network, but instead, since the function is so simple, we just create a lambda for it. And the same thing for the termination function. We're gonna create a lambda for it, and with that we have our environment model with observations. This is the transition functions for the observation that we created with the neural networks, the simple lambda for reward and termination, and the observation information and the action information. And now we have our reinforcement learning neural network environment to create the model of the environment. This is our model, the generative model. This is part of the reinforcement learning toolbox. Okay, so now we create our environment model, and we just reset the model. Now we're gonna create the options for the MBPO model. The MBPO is gonna take the environment model and also the SAC. So we're gonna number of epochs. We're gonna train the model for 1 epoch in each episode. And the mini batches, we're gonna have 50 mini batches, and each of them size 256. And the experience buffer is gonna be huge. 60,000 experience buffer. We sample from this, randomly sampled, to have a good statistical properties for the batch that we use for training. And this sample ratio is important for this particular agent, because it says, okay, this is 20% experiences are gonna come from the actual environment, and 80% are gonna come from the model environment model. So you can have a value from 0. If you have 0, then nothing comes from the real environment, and if you have 1, everything comes from the real environment. Okay, so these options are important to configure this graph that we see over here. So the first option is the rollout. Rollout is the number of trajectories. Trajectories, again, are the rows. So you have 20,000 rows of this. That's the number of rollout. The piecewise, it is used to enable the horizon increase. So as you can see, we update the horizon every 100 epochs. And then you start in 1, and then you end up in 3, as I mentioned before. In each trajectory, you select randomly 1 model first, and then 2 models, and then 3 models, and you stop there. No more than that. So this is how the strategy that the MBPO agent is going to use to generate the experiences. Okay, finally, we're going to specify the learning rate and the gradient threshold for the neural networks of the observation model. So we just put all those options in here. In the MBPO agent had the transition optimizer options, and we just patch the options for each of the 3 models. For the case of the reward function, we don't have to do the same because we are not using neural networks for them. And if you specify those options, they are ignored because we don't have a neural network in there. So now finally we create the reinforcement learning MBPO agent with the SAC agent, the base agent, the generative model, the model environment, and the MBPO options. And we finally have our agent. So I'm going to train it with 500 maximum episodes, 500 maximum steps. And yeah, so we're gonna stop when we get a reward of 470. So since we have 500 episodes and the reward for not falling is 1, you expect that the reward is close to 500. So it's a little bit less. And for 5 straight episodes, we get this score, then we're done. And there's some options for saving the status. And as you can see in here, this is gonna take 2 hours and a half, more than almost 3 hours, because of course you're training a SAC agent that has a continuous action, and also you are training 3 neural networks to model the observation. So this is expected to take a lot of time. But I'm just gonna run it. So that you can see the beginning of it, and then after that I'm gonna stop it. And just load the train model that the example provides to avoid having to wait all that time. So it started training, and you can see the status in here, the reward. The reward, as any reinforcement learning agent, starts very low and eventually gets to the 470, the expected reward. And you can see that the agent usually fails a lot at the beginning, so it's going out of bounds. My computer is a little bit slow, but you can see that it hits the boundary all the time at the beginning. So that's pretty much expected. So I'm gonna stop the training, and I'm just gonna load the train model. Okay, and now I'm gonna just simulate to get the experiences. When you train it, you need the exploration strategy, but when you simulate, you don't. You just need to, because that's only for training, to improve the training. But if you're not gonna train, that's useless. So now we're gonna have 500 steps in the simulation option, and then we're just gonna get the experience. This is basically, the experience is just basically a method of the environment. So we're gonna get the experience. Okay, my machine hung a little bit, so I had to restart. So the last thing that we did was loading the environment. The agent that is already trained. And so now let's run it for 500 steps. Again, using the eliminating the exploration policy, we're gonna use 500 steps, and we just gonna run it, get the experience again. So it's a method, and we're just gonna plot it. Okay, so let's take a look at the reward data. So let's just plot that data, and basically I don't have to plot it. Basically you can see that it's close to 1, which is good. You get a reward of 1 once you're when you have the carpal stable. So the total cumulative reward you expect to be close to 500 if it is good. So it is close to 500. So now let's plot it. Let's well, I'm gonna open the plot. I have it over here, and I just gonna run it just to see it running. And you can see that it is unlike when we started training, it was going out of the limits frequently. Now it is stable, as we have seen before, and the cumulative reward again is close to 500. So now an interesting part of this example is seeing how this fully connected layer neural network, deep neural network, is able to model the physical environment of the carpal. So we're gonna compare the observation, the actual observation of the environment with the observation that is coming out of the neural network. So for that, we're gonna simulate and again get the experience, and then compare it against the. We're gonna simulate again. It's doing fine. It's able to balance it. And now, wait, I'm not gonna go into the details of this, but what's gonna happen here is that I'm gonna collect in a couple of arrays the ground truth observations, which are the observations that comes from the experience, the actual experience, the actual environment, and then I'm gonna use the agent environment model and the action to get the observation. And that observation is gonna go into the observation prediction, and then I'm just gonna plot the ground truth and compare it with the prediction and see how close is one to the other. So let's just run this and take a look at the plots and see how close they are from each other. Okay, so we have the plotting here, and you can see that the 4 observations, so that will be I understand that they should be for the 4 elements in the observation vector, which are the position, the angle, and their corresponding derivatives. Although it would be better if the example would have labeled them, but it's okay. So you can see that it's pretty close from one another. So this shows basically that the fully connected layer, at least in this case, was able to model the physical dynamics of the environment. So we saw in this example how we can use deep neural networks to model a physical environment and get more experience than the ones that the environment is providing us, to better train a complicated agent like the soft Actor Critic agent. Okay, that's it for the video. Thank you very much for watching.